Hey, everybody, one more video lecture for material number 4 for the series. Trust me, the last one for this material. So it's about the covariance or correlation. So if you're already familiar with the concept, you can go to the assignment directly. So kind of allow me to share screen. Okay, so what is covariance or correlation? So the covariance measures the co-movement between the two axes. Okay, so if the two axes has a positive covariance, that means that the two axes turn to move in the same direction. So when one star increase, another star also increase. When one star decrease, another star also decrease. So this tend to happen for axes in the same industry because the star in the same industry, they tend to be affected by the same economic factors. So they tend to move in the same direction. So in this case, we say that they have the positive covariance. Okay, and also some stars, they tend to move in the opposite direction. Okay, and when one star increase, another star decrease. When one star decrease, another star increase. So in this case, we say that this two star has negative covariance or negative co-movements. Okay, so basically, covariance and correlation is an important factor you need to consider when you try to build your own portfolio. So for example, you need to choose two stocks, okay? And I think in order to reduce the total risk or the total up and down of your portfolio, I think you don't want to include the stock in the same industry because they move in the same direction. When you win, yes, you can win a lot. On the other hand, when one stock decrease, another stock decrease, you lose more. So increase, you gain more and lose more. So total up and down become large if you choose two axes that has the positive covariance or move in the same direction. On the other hand, if you can include two axes, they tend to move in the positive or negative, they tend to move in a negative direction, or they tend to move in different direction. So I think this is good in terms of diversification or reducing the risk. Okay, so let's first start with the notation. So this is the notation. So this is the covariance COV between two stars or two axes, A and B. So this is the return of A and return of B. So it's trying to capture the covariance between two stars return. And this is kind of confusing. We have already discussed in a previous video that sigma A is the standard deviation of A's return. And the covariance also use sigma, but in a different way. So sigma's return A and return B. So this is the covariance. So it says that tells you the covariance between stock A's return and stock B's returns. Please remember the notation. Okay, and this is the equation how you can calculate the covariance. That is, we have the E. E stands for the expected value or the average. Okay, the expected value or the mean value, the average of these parts. Okay, this is the product of deviation. So as you can see, RA subtract the expected value of RA, that is, this is trying to capture the deviation of RA, and this part is trying to capture the deviation of RB, because this is a return subject, the expected return of RB. I think maybe it's difficult to remember equation at the first sight, so let's see some example. Okay, so the calculation process of covariance is, first you calculate the expected return or the average return for A and B. Okay, first calculate the average for 2 star, and then we calculate the deviation for each case. So when RA is 5%, so what is the deviation compared to its mean value? So for B, we also calculate the deviation for each cases. And the next step is we calculate the product of RA's deviation and RB's deviation. So this is third step. And finally, calculate the average of the product of the deviation. So let's look at a little bit more on this product of deviation. So if this is positive, this means that there are two potential story. That is, this part is positive and this part is positive, or the A's deviation is negative or B's deviation is negative. Okay, let's see one by one. So in case 1, if RA's deviation is positive, that means that on that particular day, stock A's performance is higher than its average. So we can say that A performs well. Similarly, if B's deviation is positive, that means that on the same day, B also outperforms its average. So the product is positive means that they move in the same way. So when A perform well, B also perform well. The second case, so when the RA underperformed its average, B also underperformed its average. So this means that when A perform worse, and B also perform not very well. So they tend to decrease at the same time. So for both cases, they move in the same direction. So the positive sign of the product of the deviation says that the 2 stars, okay, they move in the same direction. Of course, if you trace the star for past 10 years, so maybe some days they have positive correlation. Sometimes they move in a different direction. So we can take average, which is the step 4. So we can see on average whether the product of the deviation is positive or negative. If on average this product of the deviation is positive, that means that on average these 2 stars, they move in the same direction. Okay, so I think you have a clear understanding about the calculation process compared to the concept I just introduced in the previous slide. But maybe you are still unclear, so let's go to the example. Okay, so we want to know the correlation, or we want to know the co-movement between 2 stars A and B. So we correct the past 3 months data. So in the past 3 months, for example, in January, the realized return for A is -7%. For B, in the same month, is 70%. And for the February, and A is 12%, and B is 7%. Okay, and for the March, A's performance is very good, 28%. But for B, it's kind of disaster, -3%. So I think you can immediately imagine that the 2 stars tend to move in a negative direction. But how negative? We need to calculate the variance. Okay, so just review. In order to calculate the variance, first you need to have the average value, the expected return for A and B, and then calculate the deviation for each month, and then calculate the product of the deviation. Positive product means they move in the same direction. Negative means they move in a different direction. And then finally, calculate the average. Okay, so on average, whether the product is positive or negative. Okay, first, for A, we calculate the expected return or the average return by just simply calculate average of the 3 months return. So we can see that A's average return is 11%, B's the average return is 7%. Okay, so we just use the information here to calculate the average. So based on the calculation, we know that A is 11%. And the expected return for B is 7%. Okay. Then we calculate deviation for each month. Okay. So for the first one is minus 7% subtract 11%. For this one, 12% subtract 11%. 28% subtract 11%. So for this one is minus 18%. So it underperformed its average. So for this case, the deviation is 1%. So in February, A outperformed its average. So finally, outperformed its average a lot by 70%. Okay, so this is the calculation of deviation. So you should familiar with the deviation calculation because you calculate a lot in the standard deviation calculation. So similarly, we calculate the deviation for B. We subtract by 7%, subtract by 7%. So this is outperform by 10%. So it's identical with the mean value. And this is underperformed by 10%. Okay, we have got the ingredient about the deviation of A and B. Now, the next thing we want to do is calculate the product of the deviation, right? For each month, for example, for 2019, the January, so A underperformed compared to its average. On the other hand, B outperformed because it's positive. So the product of the deviation in 2019, January is the product should be negative because they move in a different direction. So for February, the product is 0. So, and similarly for the March, so it's again, the product is negative because A outperformed its average, but B underperformed. So we already calculated the product of the deviation for each month. Okay. So this is the result. We calculate the deviation for each month and then calculate the product. So we know that for the first month, the product is minus 1.8%. Second month is 0%. And that much, we get a negative again, it's negative minus 1.7%. So we already get the each month's products of the deviation. So next step, the covariance is the average or expected value of the product of the deviation. So we just sum it up and divide it by 3. So we get the covariance is minus 1.17%. So we can say that basically the two stars, they move in the negative direction because on average, they tend to have negative product of the deviation. This means that when one star increase, another star usually decrease. Okay, this is the covariance. So to sum up, the covariance measure the co-movement of the two stars. If the two security move in the same direction, they should have positive covariance. If the two stars move in the opposite direction, they have negative covariance. So this is the image of the calculation. So we have, okay, so we have x as the x value, as axis, have y in the y-axis. So for example, this point, okay, this point is a combination of x and y. So when x is minus 4, y is 15, okay? And for this point, when x is minus 20, y is 23. So each point represents a combination of x and y, okay? So let me clear all the drawing here. Okay, now I would like you to see that the red line, okay, is the average of x. So as you can see, for the point on the right-hand side of the red line, so red line is the average. So for the point, which was on the right-hand side of this red line, that means that for those point, the x variable is larger than its average, right? So this means that for right-hand side area, they have positive deviation of x. This is for x. And for the left-hand side, they have negative deviation. I mean, in terms of the x variable. Similarly, we also have a line, which is the, give me a moment, okay. We also have line, so this is the average. The green line is the average of y. So for the point, which is on the right upper side of the line, they tend to have positive deviation of y. Their y variable is higher than this value. And for the downside, it's obvious it's negative deviation. And then if we combine these figures and this figure, we can get this figure. So the whole area is divided into 4 parts. Okay, let's continue. So for the first quadrant, or this area, so the characteristic is when x outperform its average, y also outperform its average. So what does this mean? So this means in this area, x and y tend to move in the same direction. Similarly, for the third quadrant or for this area, when the X variable underperform its average, Y also underperform. So this means that for the first and third quadrant, the X and Y, the point, they show that they tend to move in the same direction. And on the other hand, for this area, the second quadrant, so when X underperform its average, Y outperform, so the product is negative. So similarly for this area, so when X outperform its average, Y underperform its average. So the product is negative. So for this area, the product is positive. This area is positive. This area is negative. This area, the product is negative. Okay. So this is sum up for what I just discussed, that the whole figure can be divided into four quadrants. So for the first and third quadrant, the covariance should have a positive sign. For the second and fourth quadrants, they should have a negative product. Okay, so the average of the product of the deviation tell us the information about the covariance or the co-movement of two stars. And after introduce the covariance, we need to introduce another convenience measures, which is called correlation. So for example, in the previous case, we already calculate that, okay. We calculate that stop A and stop B, their covariance is minus 1.17%. So, but we know that on average, they move in a negative direction or they move in the opposite direction, but we don't know how big this number is because the calculation of covariance is highly depend on the original metric of the number. So in this case, two stars return is 7%, 12%, or 28%. On the other hand, if we consider another pair of stars, for example, there's a stop C and stop D, and both stars return is in bigger number. Let's say that they have 200%, 250%, and 500%, and D has 1,000%, minus 1,000%, and 200%. So I think the number of the original data of A and B will affect the output of the covariance. Okay, and so in order to get a more direct sense about how big the correlation is, we introduce the covariance correlation. So this is quite similar to this logic. So let's consider sometimes when we need to compare the profitability of two companies. So let's say A and B. So A's operating income is 400 and B is 200,000. So in terms of the amount of number, we say that B has higher profit. But can we say that in terms of the profitability, B has a higher profitability? No. It depends on the size, right? So if the company size is 1,000 for A and 1 million for B, then we need to standardize the profit by size. Okay, so RA is the standardized profitability measure. So once we standardize 400 divided by 1,000, we get 40%. So it's kind of 40% of return. But for B, it's only 20%. So sometimes we need to standardize something to get a more accurate estimation about for example, in this case, the profitability. And if we apply the same logic to the covariance, so I think covariance is highly depend on the original numbers. So sometimes we need to compare the covariance of two portfolio. So I think the different metric will affect the covariance. So it's difficult to directly compare. So we standardize, okay? We standardize the covariance by something, and then we get the correlation. So correlation is more convenient measure about the co-movement of two security. So in the profitability case, we use the firm size as to standardize. And in the covariance, okay, again, this is notation. So covariance is sigma RA and RB, and the correlation is standardized by the product of standard deviation of A and B. Okay, I think you must be curious why was kind of standardized by these numbers. I think this is a convenient number because, as I will explain later, so if we standardize the covariance by the product of sigma A times sigma B, we can get a very, very beautiful number, which is called the correlation. So rho here is a notation for the correlation. So to get the correlation, you first need to calculate the covariance, okay? So once you get the covariance, you standardize the covariance by standard deviation of A times standard deviation of B, then you can get the correlation. Okay, and to be more specific, the correlation measure the strength of the linear relationship between the two variables. Okay, so it measures that whether the two stop move in lockstep. Okay, when one stop increase, another stop increase. And the important characteristic of this correlation is it ranges between -1 and +1. So let's discuss the correlation in each case. So this is when the correlation is -1. So this means because it's negative, on average, the two star move in negative direction. So when one star increase, another star decrease. So let's assume that's a two star X and Y. So obvious, when X increase, Y decrease. And -1 means that you can observe a direct line, right? So when X increase 1, Y will decrease by a number which is proportional to the slope, okay? So we can observe very, very strong linear relationship. It's a straight line, okay? So -1 tell us that this two star is kind of has a perfect negative relation. It's perfect straight line. It's perfect negative correlation. And how about the second one? So in this case, it ranges between -1 and 0. So in this case, yes, I think not all the point lie in the green line, but we still can draw a green line. Approximately, it's kind of the point line surround the green line. So it still says that they has a negative correlation, but not as strong as the -1 case. So in this case, yes, we can draw a straight line, but no other point lie on the green line. So we say that the correlation is negative, but it's not so strong as the number one case. Okay, and similarly, if this is a positive one, that means that they have a perfect make positive relation, perfect straight line. Okay, perfect positive. And similarly, this is a positive correlation, but it's not so strong if this range between 0 and 1. Finally, if the correlation is 0, that means that you cannot find any pattern between x, y's movement. So we cannot draw this line, we cannot draw this line, we cannot draw a straight line to capture the co-movement between two stars. So I just need you to remember that correlation is a standardized covariance, and it's standardized covariance by the product of the standard deviation of A and B. So why we standardize by this number? Because by standardized covariance by the product of A and B standard deviation, we can get a beautiful number, which is correlation ranging from -1 and +1. So if the two stars, the correlation is -1 or +1, we say they are perfectly correlate with each other. So if the number range between 0 and 1 or 0 to -1, we say that they are positively or negatively correlated, but in a less extent. So if the correlation is 0, near 0, that means that they have very weak correlation. Okay. Now let's calculate the correlation, okay? So this is the Manaba in-class test. So you need to calculate. So let me repeat the process of calculating. So we need to calculate variance first. So how to calculate variance? We need to calculate the mean value. Okay. So first calculate the average of A and calculate the average of B, right? And then please calculate the deviation. And of A and deviation of B. Then calculate the product of the deviation. And the average of the product is the covariance. So to calculate the correlation, you need to standardize the covariance by A and B standard deviation. That means you also need to calculate standard deviation of A and B by yourself. Finally, you standardize the covariance by standard deviation, you get the correlation. So let me go to the previous example. So based on the, so this is the previous example. So we already get the covariance is minus 1.17. And if we standardize this number by the product of the sigma A times sigma B, so, okay, let me see the calculation of sigma A and sigma B. For sigma A, it's around 14%. And for sigma A, it's 8%. Then the correlation rho equal the covariance divided by sigma A times sigma B. Okay, so this is minus 1.17% divided by 14%. times 8%. So it's approximately minus 0.999. Okay, it's approximately -1. So this means A and B, they are almost perfectly correlated with each other. Okay, that's the end of the final lecture for this material. Now it's your turn to do the calculation. Thank you.